to be giving a presentation on terraforming Venus. The same approach that I'm going to be describing for Venus could also apply to other similar planets that we might run into in other star systems. My name is, again, Ken Roy. On the screen, you see my email address. Because this isn't live, you can contact me at this address with any comments or questions relating to this presentation. And on that note, let's get started. Terraforming basically means Earth shaping. It's the creating of habitable worlds out of essentially sterile planets or moons, making a planet that is inhospitable to human life, converting it into a planet that hosts human life and also humans. So terraforming comes in two basic types. We have planetological terraform, where you essentially make an Earth 2. It's stable over geological time periods, and you don't really have to perform any maintenance once you've got the planet terraformed. That's more difficult. You've got to have just the right candidate to terraform such a planet. I'm not sure we have such a planet in our solar system, but we might run into other planets like that around other stars. The second type is habitable terraform, and what that does is make a planet habitable. We use artificial shortcuts, geoengineering, megastructures. It will require periodic maintenance and replenishment. On the other hand, it's usually easier and quicker than the first type. And I'll be talking mainly about the second type, the habitable terraform. To give you some idea of what a terraforming effort looks like, this is a fairly recent picture of Mars. And if we wanted to terraform it, either using one of the other methods, then what we want to do is convert this into this. It's a fairly extensive and challenging effort. It's not going to be quick. It's not going to be easy. But the reward is you end up with an entire planet that you can live on. Now, one of the questions we run into fairly quickly when we start talking about terraforming is gravity. How much gravity do humans need to survive, to thrive? And we have a lot of experience with the 1G environment that we're all sitting in right now. But we don't have a whole lot of experience with other levels of gravity. The International Space Station is perhaps the one exception to this. We have fair amount of experience with 0G or microgravity, but that experience is not real positive. People who spend a month or two at the International Space Station have fairly significant changes in their muscle system and skeletal system and cardiovascular system and other changes as well. One researcher noted that the effects seem to mimic accelerated aging. NASA is working on that, and they're looking at a regime of exercise and drugs that seem to mitigate some of the worst effects, but still, it's not for the faint-hearted, and certainly it's no way to live for the long term. So how much gravity do we really need? Given those two examples, we really can't say. And it may be that people need different amounts of gravity at different points in their life. We have no idea how much gravity a pregnancy requires to be brought to term. We do know that children seem to need gravity in order to learn how to balance and in order to learn how to walk and run. And it may be that older people need less gravity than that to survive very comfortably. But we just don't know. So what is X? What level of gravity is necessary for humans to survive and thrive? And we're just going to have to run the experiment and find out. So I bring that up because Mars typically is considered, a good planet for terraforming, and we can do a lot of things to it, make the air breathable, import water, but we can't really change the gravity. Gravity is about 0.38 that of Earth, and oddly enough, Mercury has pretty much the same gravity, so 0.38 that of Earth, and that may be enough. I mean, people may be able to thrive and live very comfortably in that gravity If not, if it turns out we actually need more gravity, then really the only other candidate here in this solar system is Venus. Its surface gravity is about 0.9. So 90% gravity of Earth, that probably would address the gravity question, we think. Yeah, Earth and Venus very similar in size, compared with Mars, Mercury, Pluto. Earth and Venus are pretty good sized worlds to work with. So a few more details about Venus. We have mass, radius, surface area, gravity, pretty similar to Earth. Now, one thing it doesn't have is any kind of magnetic field. It's closer to the sun, of course. Its axial tilt is a little odd. It's either extreme, think of it as a 177-degree tilt, or you can think of it as a 3-degree tilt, but it spins backwards. In other words, the sun will rise in the west and set in the east. That's that's not a big issue. The year is 225 days, Earth days. That's again livable. That's not a big problem. The solar day, however, is 116 or 117 Earth days. So from sunrise to sunrise on Venus, it's going to take 116 or 117 Earth days. And that could be a problem. Okay, so basically, if you want to terraform Venus, you need to reduce its atmosphere. It has a very, very thick atmosphere. If you're standing on the surface, it's going to be about 95 atmospheres. So the atmospheric gases on Venus is roughly about 95 times that on Earth. So there's a lot of gas we're going to have to deal with, most of which is CO2. The surface temperature is 850 degrees Fahrenheit. So if you like pools of liquid lead, you can probably find that on Venus. In order to terraform it, we're going to have to deal with the massive amounts of CO2 in the atmosphere. And actually, nitrogen turns out to be a problem. It's got 3 to 4 times as much nitrogen as Earth does. It's a small part of the atmosphere just because there's so much CO2. We're going to have to import a lot of hydrogen in order to make water. Water is relatively important for a habitable planet. Shorten the Venetian day, again, 116, 117 Earth days. It's hard to imagine how that world would actually work. And then we might want to resculpt the planetary surface to build ocean basins and mountains and continents. Here's again some more data on Venus. One thing to keep in mind is it has no plate tectonics. Plate tectonics is a result of a molten core and a crust which is not solid. The crust on Venus is completely frozen. It doesn't move. It does seem to have a molten core, which results in large shield volcanoes that just stay put, but they just get bigger and bigger. The crust of Venus is shown there on the left, very, very similar to what we have here on Earth. Again, temperature is pretty high. It's going to be a challenge. Before we get too far into the various terraforming schemes, let's talk about the Sun-Venus L1 point. That's a point on the line between the planet and the sun, where because of gravitational interactions, it's actually stable. You can put something at that point and it will remain at that point. If that thing happens to be very big, it can actually block some of the sunlight that would otherwise hit the planet. So sometimes we refer to this object as a solar shade. And if it's big enough, it could actually block 100% of the sunlight that would otherwise hit Venus. This is going to be a useful technique for a number of terraforming schemes that we're going to talk about here. Now, the solar constant at Venus is about 2.6 kilowatts per square meter, which is significantly more than what we have here on Earth. If we coat this solar shade with solar cells and collect the light, convert it to electricity, assume a 10% efficiency, we're terawatts of energy to work with. And any terraforming project that we undertake is going to be time consuming and energy consuming. Well, here's the energy that we could use on this. And this is kind of a twofer. If the sun shade is big enough, we will cool the planet and we will have the energy we need to work with. The first approach I'm going to talk about was developed by Birch, his first name right now, so we just call it the Birch approach. And what he starts off is building a sunshade at the Venus-Sun L1 point, like we just discussed. And that results in a total blackout on Venus. Initially, Venus cools about 5 degrees C per year. And he estimates in 100 years that the planetary gases would be about 0.0 degrees C. In other words, water would begin to freeze out. In 200 years after that, it's actually cold enough where CO2 begins to solidify and freeze out and fall to the surface. So that creates a big blanket of solid CO2 on the surface of the planet that you're going to have to deal with at that point. Go to the surface and either bury it or export it or convert it into something else. But there's a lot of it. And also, nitrogen is still in the atmosphere at this point, but it's 3 to 4 times what we have here on Earth. So we may want to export some of that as well. And we're going to have to import a lot of hydrogen in order to make water. We can take the oxygen from the CO2, make water, and then release O2 into the atmosphere. And at that point, you open up the sunshade some, import Earth life, and you've got a habitable planet. He doesn't really address the Venetian day problem, but this is one scheme that has been proposed and is out there. Another scheme is the Oberg fog approach. And here you start with an atmosphere of CO2 and nitrogen. And then you import hydrogen. Then you have either organic beings or organic systems or even mechanical systems that break up CO2 and combine the oxygen with the hydrogen to make water. And you slowly, over time, build up enough water that you can import cyanobacteria, which is very useful because what it does is take CO2 and water, which we've just put in the atmosphere, and sunlight, and it breaks up the CO2. It releases the O2 into the atmosphere, and the carbon just rains down to the surface, so it begins to precipitate out. And once this has gone on long enough, you've converted this atmosphere, CO2 and nitrogen, into this atmosphere, which is water, O2, and nitrogen. Now, the next step is to build a solar shade, like we were talking about earlier. This cools off the planet, and once it gets cool enough, the water begins to condense and rain out, and then that fills up the ocean basins. And finally, you've condensed out most of the water, and you end up with a final atmosphere of nitrogen and oxygen. And you also have ocean basins full of water. You've also got a big layer of carbon on the surface of the planet. Now, he doesn't really address, again, the long day problem. And also, he's got a lot of nitrogen here that he's going to probably have to dispose of somehow. He also requires a lot of hydrogen. To give you some idea of how much, 4 times 10 to the 19 kilograms of hydrogen. That sounds like a lot, but it's really just a minor quantity from one of our gas giants, Jupiter, Saturn, etc. So that's a lot of hydrogen. Also, calculating how much carbon has been rained out, you're going to end up with like a 100-meter thick layer of carbon on the surface. Now, Stefan Gillett has offered a modification to that where you import calcium and magnesium, and that combines in a roundabout way with CO2 and forms calcium carbonates and magnesium carbonates, which, we sometimes know those as rocks. And this reduces how much hydrogen you need by about a factor of 4. But you need lots of calcium and magnesium. You might be able to get that from the crust. You might have to import it. It looks like mercury might be a good place to take it from. And the time frame for this approach, they estimate 10,000 to a million years to get it going. Now let's talk about how much hydrogen we're talking about here. 4 times 10 to the 19th kilograms. Let's assume we have a tanker that has a sphere that could hold liquid hydrogen that's 4 kilometers in diameter. And we're going to need to make close to 17 million trips with such a tanker, each pushing a massive weight. And the fuel to propel these tankers around is probably going to be 2 or 3 times this number. And that's going to be a big task. So when we say import hydrogen, understand that it's going to be a big effort. Neither one of those approaches talks about how we might spin up a planet or shorten the Venetian day. There's the formula, and if you crank through the numbers, there's various solutions. But let's assume we have a 170 kilometer diameter impactor, an asteroid, or maybe a comet, and it comes in at 25 kilometers per second, which is probably what you'd get if it came from the asteroid belt. That increases or decreases the planetary spin by 1.4 days. Again, if we wanted to, make it pretty much Earth-like, we would have to have 82 such impactors. Now, there's lots of asteroids out there, but there's not a lot of asteroids of that size out there. And I would suggest that number of asteroids of that size are probably more valuable as resources rather than as impactors. But it does deliver a lot of H2O, H2 silicates, and we can use it to shape the surface if we want. But it also delivers a lot of energy to Venus, and it's going to heat up the surface, perhaps enough to actually turn the surface into a molten state, in which case you're going to have to wait several thousand years for it to cool off again to continue your program. So the two approaches I've talked before have big deficits, big problems. But let's take a different tact here. Here we have a description of the Venetian atmosphere. Over here we show how much carbon dioxide we have, which is 96%. We have a lot of nitrogen, sulfur dioxide. We have some argon. There's actually a tiny bit of water in the atmosphere as well. And there's a little bit of helium, a tiny bit of helium, but there's helium in the atmosphere. It probably derives from the solar wind that impacts the planet and is just absorbed into the atmosphere. Now, a tiny fraction of this helium is going to be helium-3. And helium-3 looks to be a very potentially valuable fusion fuel. And there's a lot more helium-3 in the Venetian atmosphere than is on the moon, which is typically where people start talking about mining helium-3. So, keep that in mind. Okay, the green line here is the temperature of the atmosphere with altitude. Here's the altitude in kilometers, and here's the temperature in degrees C. So at the surface, it's fairly warm. But once you get up here around 60 kilometers, you'll notice it approaches this blue line. This blue line is the temperature altitude for Earth's atmosphere. Now at this point, they're actually pretty close, and that looks intriguing. It turns out if you look at the height and the temperature and the pressure around 50 kilometers up, you end up with a temperature fairly Earth-like and pressures fairly Earth-like. So again, I think it was Jeffrey Landis who said that the problem with Venus is not that the surface is too hot, but that the surface is too low. If we could raise it up 50 kilometers, we would have actually, very Earth-like conditions. Now, it would still be CO2, but it would be a lot better than what we have now. And this suggests the idea of floating cities on Venus. This was originally published, as near as I can tell, in a Russian paper back in '71. And this is a graphic from that paper. It turns out if you're at, 50, 55 kilometers above the surface, conditions are very Earth-like as far as temperature and pressure. But you're still dealing with CO2 out here. But if you create an atmosphere of oxygen and nitrogen in here, it's a lot less dense, and it can actually serve as a lifting gas. So if you have a big enough volume with this lifting gas, you can support a fairly robust structure, and it just floats around in a very comfortable environment. So that's a thought. Here's another cloud city that you may recognize, and there's no reason we can't build cloud cities that look just like this. So floating cities in the atmosphere of Venus is something we can do probably very, very near term, well, relatively near term. And again, because of the CO2 atmosphere, we have lifting gases of oxygen, nitrogen. So it could actually be a pretty interesting place to work. And what's also important is that at that altitude, you still have enough gases above you to provide good radiation shielding. So it's a good research location. And it's a good location if you want to do some helium-3 mining. So again, if you're looking for an interesting setting for a science fiction story, think about a cloud city floating around in the Venetian atmosphere. Here's another image. I think NASA put this one out, showing a little Zeppelin craft approaching this is the Zeppelin craft approaching a cloud city. So we can probably do cloud cities pretty easy. The basic terraforming techniques I've talked about before look like they have problems. It'll be expensive, it'll take a long time, and there are other issues that they don't address. But can we kind of marry those two together? And the answer is yes. Here's an approach that was presented at the Interstellar Research Group Symposium in Wichita in 2019. And the paper's available. If you want a copy of it, just send me a request at my email address, and I can send it to you. But the basic idea is that we build a material shell above the surface of Venus, much like a cloud city, where the pressure and temperatures are of our choosing. And we create an Earth normal atmosphere above the shell. Below the shell, most of the atmosphere is untouched. We leave that as is, so we don't have to mess with it. 97% of the original atmosphere is going to stay right where it is. And the pressure under the shell supports the shell structure, and it's actually, a fairly big shell, 3 times the land area of Earth. So that's the basic idea for kind of a shell terraforming approach. But can we build such a thing? If we have a pressurized sphere, we know how to calculate the tension in the sphere, and that's this formula here. Here's what the variables mean. If we assume that we have 3.1 atmospheres under the shell, and we want 1 atmosphere on top of the shell for a net of 2.1 atmospheres, pressing inside the shell. The radius, let's just pick 43 kilometers above the surface. And let's assume we have 1 meter of steel to make it, a durable shell. I use steel to illustrate the idea. In reality, you could probably use better materials, carbon fiber, graphene, stainless steel, titanium, some combination of the two. But for our purposes, I'm just going to assume we're using 1 meter of steel, and show you what some of the numbers turn out to be. If we plug in the numbers, here into this formula here, we end up with the tension in the sphere itself, in the wall of the spheres, of 64,000 MPa. MPa is just a unit of stress. Steel has a tensile strength of about 370 MPa. So at first glance, this looks like if we tried to build this, it would just pop like a balloon. But there's another force in play, and that's gravity. Because we built this shell around the planet, the gravity is going to be pulling on the shell. And we know how to calculate the compressive strength of gravity pulling on a spherical shell. And here's the variables. Again, here the density, this is what typical steel would weigh, about 8,000 kilograms per cubic meter. Again, we assume diameter is 1 meter of steel, and this gives you the total mass that we're dealing with. It's a lot of steel. And here, the compressive stresses is equal to 210,000 MPa. But steel only has a compressive strength of around 370 MPa. So again, it looks like the gravity would just simply crush this like a cooked eggshell. But if we're clever, we can actually get these two stresses to cancel out because they're both in play at the same time. We have compressive forces from gravity, and we have tensile forces from the pressure contained under the shell. We can make these two equal by varying the thickness of the shell or just adding dead weight on top of the shell. In this case, it turns out that if we add 11 meters of dry regolith to the top of the shell, the forces exactly equal out. The net stress within the shell is zero, or really close to zero. And so we do have the possibility of building a shell that will withstand the forces that the planet will impose on it. But the question comes up: okay, well, if you build this thing, is it stable? Will it stay put if you build it? And the answer is yes. We've published a paper on that in the 2014 JBIS that talks about shell stability. And it turns out if the pressure gradient, as it varies with altitude, varies faster than the gravitational gradient as it varies with altitude, then pressure will indeed begin to restore any shell that's displaced, as is shown here. The pressure will push this side of the shell away, and this part of the shell will see a reduced pressure, and it will be pulled back to a central position. So yeah, the shell will be stable even if it doesn't have columns or cables connecting it to the planet. As long as you can maintain the appropriate pressure. There are different places where we can actually build this shell, and here's some various solutions. For our illustrative purposes, I'm going to choose 43 kilometers above the surface. There, the initial temperature of the gas is about 96 degrees C. The pressure at the shell, as we have talked about before, is 3.1 atmospheres. And the shell, if we assume 1 meter thick steel, is about 8 metric tons per square meter. In order to provide enough mass so that the stresses equalize, you need about 24 metric tons per square kilometer, or square meter, sorry. 24 metric tons per square meter. So it's going to be a fairly robust shell. Okay, well, how would we build such a thing? We can't, put in scaffolding and build it. So let's take a different approach. Let's think in terms of a geodesic sphere. Most of the components of a geodesic sphere are hexagons. You have to have a few pentagons in order to make the concept work. But here, let's build hexagons that have 20 kilometers on the side. That means the area is about 1,000 square kilometers. The mass is pretty hefty, about 8.2 10 to the 9 tons, metric tons of steel. We also need to put atmospheric processors on this thing, and in order to get it to hover where we need it, we're going to have to support it with a big balloon, and we'll talk about that here in a minute. And it turns out you need about 450,000 of these things. No one ever said terraforming was a minor effort, but sometimes the rewards are worth it. Okay, so the Venetian shell, you know, shown in side view. Here's the shell element. This is a meter of steel. The atmospheric processors are built into this thing, maybe on the surface here. And we have a balloon about 2 kilometers tall. Again, the sides are about 20 kilometers. So this is not to scale, but close. And with our chosen atmosphere, this was enough that the shell can actually hover around. We can use hydrogen as a lifting gas, and helium is not actually too far behind. Again, because the Venetian atmosphere is so very, very thick. So the initial shell that we're talking about here is about 8 metric tons per square meter, and again, we're talking a lot of meters. So that's the elements. So we can actually build this thing in orbit, or these things. There are going to be lots of these things in orbit, and lower them into the atmosphere where the balloon is deployed, and then it begins to seek its designated altitude. Again, here we'd probably have to import hydrogen for that, but we're going to need hydrogen anyway for other things. Or we can build it on the surface using Venetian resources if we can figure out a way to deal with the temperatures. And here we'll either have to import hydrogen or extract a lot of helium. Okay, so once we have these things floating around about 43 kilometers above the surface, then they assemble themselves or are assembled into the shell. And we talked about atmospheric processors. Well, those are, among other things, very, very big fans. So that gives you some ability to maneuver. And so these things link up and eventually complete a geodesic sphere around Venus at the 43 kilometer altitude. You may want to release some of the hydrogen so the shell goes into compression. You have the shell pretty well constructed, then you weld the elements together and you've got your shell. Again, atmospheric processors used to maneuver these things. Admittedly, putting in the last piece might be a challenge, but hopefully we'll have the technology to do that when we get around to doing this. Now, these atmospheric processors that I talked about before are now going to begin to take the atmosphere, which is a Venetian atmosphere above the shell, and compress it and inject it below the shell. What we want to do is reduce the 3.1 atmospheres of Venetian gas above the shell to 1 atmosphere of Venetian gas. And we do that by injecting the excess atmosphere below the shell. And as we do this, as the pressure above the shell goes down, the shell itself will go more and more into tension, and we compensate that by releasing gas from the balloons, and eventually the balloons are unnecessary as the pressure approaches 1. And at that point, in order to maintain an allowable stress in the shell, we have to start adding mass to the top of the shell. So we start off with 8 tons per square meter, and once we're done, once we reach 1 atmosphere of pressure, we're at like 24 tons per square meter of material on the shell. Okay, so to convert the 1 atmosphere of Venetian gases that are now present above the shell to an Earth normal atmosphere, we have to process a lot of CO2. So again, our atmospheric processors take CO2 from above the shell, break it up, release the oxygen back above the shell, and just throw the carbon on top of the shell. So we keep that. Again, there's a little bit of SO2. We convert that to sulfuric acid, which is a very useful industrial gas, and get rid of the acid rain problem. The Venetian shell, once we've done that, we have to then inject nitrogen most of the nitrogen we need is actually below the shell. So again, our atmospheric processors come in. We're going to have to process a lot of Venetian gases, extract the nitrogen, and inject that above the shell. Now here we're dealing with gases that are present on Venus already. We don't have to import any nitrogen or any oxygen into the Venetian system. We will have to import hydrogen if we want water, but we've talked about that. Argon, we may not be able to achieve the percentage of argon in the Earth atmosphere. On the other hand, argon is essentially biologically worthless. So we can probably just dispense with argon, replace it with nitrogen. And yeah, we're going to need a fair amount of nitrogen to do all of this. But this is only about a third of the nitrogen available at Venus. So what will the final configuration look like? There's lots of possibilities. This is just one that I would suggest. Here's the original shell. It's probably been beefed up and reinforced. Maybe it's got a lot of graphene and carbon fiber on it now. The atmospheric processors, other utilities are located on the shell. And here we're going to have arches and columns supporting a membrane, maybe a steel or aluminum membrane, or maybe advanced material membrane. And here's where we put our ground level, rocks, dirt, and this is going to be the top layer of soil, which is where our biosphere is going to be based out of. This tween space here could be very useful for transportation, energy production, utilities, industrial production, storage, and again, I mentioned transportation. So all of that is stuff that we can put in this tween space, allowing the surface, the actual surface, to be more of a garden. Now again, it's about 91 C here, so we want to slow up heat transfer into the shell. So we're going to need a fair amount of insulation, and aerogel might be just the thing for this. Now this allows us to inspect the shell both top and bottom for any signs of corrosion and repair any problems as they develop. But again, this is just one possibility. There are many others. Just a quick note on living soil. The dirt that you go outside and walk on is composed of 45% minerals, sand, silt, clay. We want to build that on our Terraform Venus. So this stuff we can get from the surface of Venus. Organic material, that's just going to have to be grown and put in the soil somewhere, and then water and gas make up the rest of the soil proper. But there's also a lot of bacteria in soil. If you go out there and look at a square kilometer of soil, you're looking at 45 to 400 tons of bacteria and a little bit more fungi. Now, very fertile soil has a good balance between bacteria and fungi, and there's a symbiotic relationship between the fungi and the bacteria and the plants. And it's a very, very complex subject. Just understand that it is complex, but it is doable. We can't have seas. In fact, it looks like the habitable planets are going to need seas of some type. And here, again, because of our mass loading limitations, we're limited to 16 kilometers of water. But again, it allows us to inspect the shell at the bottom and at the top. And the seas can be, as big or as little or as numerous as we like. And even a small leak would not be the end of the shell, because the sheer volume of material involved is so massive that gives you plenty of time to plug up small leaks as they occur. This much water, again, is going to require a lot of hydrogen, probably not as much as our earlier example, but a lot of hydrogen. Cell corrosion issues, again, as long as you can inspect it and fix it, you're probably in good shape. Just understand, big leaks lead to big problems. If an asteroid hits the shell, that could be a big problem. So you're going to have to be watching the skies pretty closely. But you can't have seas. You can't have you can't have oceans, but you can't have seas. And marine life to any extent that you want. So the final steps, we talked about spinning up the planet before, and how difficult that is. We don't need to spin up the planet. We just simply need to spin up the shell. It's not connected to the planet in any real sense. So with our atmospheric processors, we can begin to spin this shell completely independent of Venus itself. And we can easily achieve a 24-hour day-night cycle and even mimic Earth's axial tilt. At that point, we can adjust the solar shade to simulate an Earth temperature profile. Again, we're still going to have a lot of solar shields up there, and if they're providing energy, then that may be the energy source for Venus. The sun will look kind of odd to an Earth dweller. Of course, it will be bigger, and with a solar shade there in the middle, it'll look like a dark spot. It might look like a big eyeball kind of looking at you. Establish a hydraulic cycle. That means we need to warm up the water enough where the water evaporates, forms clouds. Clouds come over the land, and they rain on the soil, forming streams and rivers and flowing back into the sea. We talked about making living soil. That's going to be a challenge. No way to minimize that. It's going to be a challenge. And introduce Earth life. That's going to be part of living soil effort. We can also build an artificial moon if we really get ambitious. It doesn't actually have to be a moon, just a big balloon, big balloon, and that can mimic Earth's moon as far as its period, size, its brightness, and might be very Earth-like. So we can at that point begin to move in and set up shop. Not just humans, but also probably most life that we have here on Earth. So humans and Earth life would have two homes rather than one. A couple of open issues, open questions. There have been reports that there may be life on Venus already. Don't know that for a fact, but if there is, then we run into an ethical question. Is it ethical to terraform a planet with life on it? And I'll leave that question to others. Who owns Venus at this point? I don't really know. What happens under the shell? Again, with the shell, all the gases under it are now in complete darkness. And over time, I imagine they would begin to cool off. And what that will mean is the pressure will decrease. The shell may go into more compression than you would like. And you can counter that simply by dropping some of the mass from the shell onto the Venetian surface. Atmospheric processors, again, those are complex machines, but they're very similar to compressors and big fans. They need the capability of separating elements of the gas out, like nitrogen from a stream of CO2, and there are different ways to do that. But if we can easily separate out helium-3, then that gives us a way to probably fund this whole enterprise. Again, if helium-3 turns out to be a great fusion fuel. We're going to have to monitor the shell stress in real time and maybe set up some kind of ability to move mass around again in real time. Maybe some kind of pump water system. And again, this shell is going to require continual maintenance and monitoring for the duration of the time that we use it. This picture was taken, I think, in Montana, and I've always enjoyed it. But in 1,000 years, if we get ambitious, this picture could represent a scene on Venus. So if you're looking for an interesting setting for a story, Venus might be just the place to consider. And why would we want to terraform a planet at great expense and great effort when we've got a perfectly good world here? Well, I would suggest that if there were smart dinosaurs 65 million years ago, they were probably asking the same questions. And it looks like they made the wrong choice. So having more baskets to put your eggs in is not a bad thing. Okay, so those are some thoughts on terraforming Venus. I hope that has been interesting. And there's my email address. If you have any questions or comments, feel free to drop me a call. Again, we've written up the paper using the shell approach to terraform Venus. I think that makes it a lot more feasible. A little bit of out of the box thinking, but certainly feasible. Or at least I don't know of any reasons why it can't be done. So again, hope everyone enjoys LibertyCon, and I hope to see everyone in person next year. Y'all take care.